Alright, so this video is going to be about how this new concept of work actually relates to our old concepts that we've been talking about of energy. Because we saw that work has got a unit of joules, which is the same thing that energy has as its unit. So work and energy have to be related to each other. So this video is going to be about how they relate. So let's start off with a little example. Okay, we have our trusty physics book here. All right, and there's our physics book, and it's kind of heavy. We know it's kind of heavy. It's somewhere maybe 5 kilograms. It's probably more than that, but we're going to say it's 5 kilograms. Now I'm just going to estimate here. I'm going to use G is equal to 10 instead of 9.8 just to help me out. So that means this thing weighs about 50 newtons. Okay. Now let's say you dropped your physics book on the ground and you had to pick it up. So we're going to pick it up and we're going to bring it up to about right here. Okay, and let's say you raised it about 2 meters off the ground. In fact, I'm going to do that in a different color. Okay, 2 meters off the ground. So we're going to say maybe you raised it with a constant velocity. Actually, turns out it doesn't matter, but let's just say it's constant velocity. So what is the amount of force that you had to apply to the physics book in order to raise it? Well, if it's constant velocity, then it's going to be 50 newtons. So how much work did you do in raising your physics book? Well, we just learned that it was force times distance to get work, so that'll be 50 newtons multiplied by 2 meters, and that gives us 100 joules of energy. Okay, but now we've raised this thing 2 meters up off the ground, so that means it should have some energy, especially if we're using the reference point of the ground as being 0. So what kind of energy does it have? Well, it has potential energy. Okay, UG, and we know that we can actually solve for potential energy with an equation that says mgy. So let's plug that in there. So we're saying 5 kilograms, and we have a gravity of what we're using of 10 meters per second squared, and y in this case is 2 meters. Okay, well maybe you've already seen it, but take a look. 5 times 10 is what? Well, that's 50. And then take that 50 and multiply it by 2, and you get the same 100 joules of energy. So is it a coincidence that the amount of work that you did to raise the book is now the amount of potential energy that you gave it? It's actually not. It's not a coincidence. It means that the work that you did is equal to the potential energy that the object now has. So basically, you used some of your energy to perform work, and we know that energy can't be lost or destroyed in any way. So where did that energy go? That energy went into the potential energy of the book. Okay, so you've decreased some of your energy. Now you have to go, I don't know, eat a bag of potato chips to get that energy back. Okay, but that energy has now gone into the potential energy of the book. So if we use our energy bar charts to look at this situation, we have our before it being on the ground, and we have UG, we have K, we got other stuff in there, but these are the only ones that we really care about. And if it's on the ground, it has no UG, it has no mechanical energy. Okay, then we did some. Well, let's just take a look at the after. That's what we're used to doing. So after it has mechanical energy because it has potential energy. So it's got all this UG, has all this mechanical energy. So mechanical energy before usually equals mechanical energy after. Okay, and that's for an isolated system, but in this case, look, it doesn't actually equal. It's not an isolated system. Why isn't it an isolated system? Well, we interfered by forcing this book, by increasing its potential energy, we interfered. So maybe we have to include one extra step, and that extra step is how much work was done. Okay, so now we're going to have this new column here that is going to be how much work is done, and we did that amount of work, the same amount of potential energy. Okay, work and potential energy is the same. So if you take your before mechanical energy and add it to the amount of work that was done, then that equals the amount of mechanical energy that you have after. So I'm actually going to take this, I'm going to erase it, okay, and I'm going to erase this side too. And now we can say that the amount of mechanical energy before plus the amount of work that was done equals the mechanical energy after. And that right there is the work energy theorem. So the work energy theorem basically just states that work is the intermediary in transforming your energy. If you have work, that's going to increase or possibly decrease the amount of mechanical energy that you have in your system. It transforms your energy from one thing to another. Okay, what if we drop the book back down? Okay, well, it would be basically reversing this what am I trying to say? Reversing this process. Okay, potential energy would go down, and it would go back down to zero. You'd have zero mechanical energy, and that would actually be the work being negative, and you would transform it into some kinetic energy, actually. Okay, but the same process still holds. Okay. Well, what's the situation where we can actually decrease mechanical energy? Well, up until now, we've been saying no friction, no friction, no friction. So what if we actually put some friction back into it? Okay, here's a table. Okay, rough, maybe wooden table or something. Have our handy-dandy physics book. Okay, there we go. And this physics book, maybe you were just throwing it onto the table, so it's got some velocity. All right. Now, and we know that tables that have friction, you throw the physics book on the table, it slides for a little bit, but eventually it stops. Okay, V equals 0. So what does that look like on our energy bar charts? Well, we have our before. Okay, our before, maybe let's set the reference point to be at the table so we don't have to worry about UG. We have lots of kinetic, okay, and therefore we have lots of mechanical. It's the same amount. And then what happens? Well, our after looks like this. It has no kinetic, still has no potential, and now our mechanical energy is 0. So what happened between the before and the after? Well, we have friction, and friction is a force, and that force is backwards relative to the motion of the object. That's the force of friction. So the force of friction, which we know, just to review, is mu times the normal force, is doing work, right? Work is the force of friction multiplied by the distance that it slides. But because it's the cosine of theta, that means that work is actually going to be negative because it's the cosine of 180 degrees. The distance that this thing goes, which I'm going to put in red, okay, there's our displacement vector. And our force of friction right here is they're 180 degrees away from each other. So the work that we have is negative. Okay, so if we put in our work column, then that work is actually going to be really far down negative. Okay, so if you add this work to this kinetic energy, and we're assuming about the same amount, then you get no kinetic energy, no mechanical energy, and that's your after state. So if we wanted to write down the equation for this, it would be mechanical energy before plus the amount of work, which that work is negative, equals the mechanical energy after. So mechanical energy before is the kinetic energy. Kinetic energy before plus the work due to friction, which remember is a negative value, equals 0 because you have no mechanical energy afterwards. And therefore, the work done is actually the kinetic energy that is started off. So the amount of work here is not potential energy, it's equal to the amount of kinetic energy that you've lost. So this is again showing us that the work done equals the kinetic energy, and actually it's the change in kinetic energy, right? The amount of kinetic energy that we lost. I'm going to write it this way, kinetic that we lost. Okay, so it's a change in kinetic energy. That work changed our energy. Just like over here, that work changed our potential energy. This is the amount of potential energy that we gained. So work is that middleman step to change your potential to your kinetic.